Okay, so we are going to be talking about the inverse trig functions. Okay? For example, if we have y equals the sine of x, how do we find an inverse? What do we do algebraically? Do you remember? We switch x and y. So if we want to talk about the inverse, we would talk about x equals sine of y. Okay? If we were to solve for y, we would have to use the inverse. We can't take the y out of the sine. We can't divide by sine and leave y, they're not tied together that way. We would have to write it as an inverse. Do you remember this notation, or do you remember seeing this notation in Algebra 2? Yes. That sine with the -1. You've also seen it on your calculator, right? Sine -1, cosine -1, tangent -1. Those are the inverses. Okay? What's happening with an inverse, let's talk about up here. Here in our normal function, our input was an angle and our output was a ratio. The sine of pi over 3 equals radical 3 over 2. So we input an angle, our output is a number. Okay? Now, when we're talking about the inverse, our input is a number, oftentimes a ratio. Our output, so our answer, is going to be an angle. Okay? So our input is a number, our answer is an angle. So first let's get familiar with each of the inverse trig functions. Now, I am going to talk about the sine, cosine, and tangent graphs. I know that you haven't seen them before, and we'll work on graphing them next week, but just roll with me here, okay? Now, what have you noticed about the unit circle in terms of the sine values? When we look at the y values of the unit circle, they don't get bigger than what? What's the biggest those sine values get? All of the y coordinates of our unit circle. What's the biggest one? 1. What's the smallest one? -1. Okay? So if we were to look at our sine graph, it actually looks like this. And like I said, we will graph it next week. All right, but all of our sine values bounce in between -1 and 1. All right? Well, if we were to flip this along the x equals y line to make this an inverse, is this an inverse? Or excuse me, is this a function? No, it's not. It doesn't pass the vertical line test, right? So in order to force inverse sine to be a function, we have to restrict it so that it does pass the vertical line test. Okay? So here's some information about the inverse sine. Here are 2 different ways you're going to see it notated. Arc sine means the same thing as sine inverse. Our domain is only from -1 to 1. So that means our inputs can only be between -1 and 1, just like the unit circle values. Okay? Oh, man, I didn't get those fixed. And our range, our y values only stretch from -pi over 2 to +pi over 2. Okay? I don't really care if you know the graph or not. That's not a big deal. What you need to know is right here. Our inputs are only going to come between -1 and 1, just like those unit circle values that we have. And our outputs can only come from negative pi over 2 to pi over 2 because that's the only way this will be a function. Okay, so let's think about where those values would be. Let's think about our unit circle. Where's negative pi over 2? Okay, it's the same thing as like 270, right? So negative pi over 2 is here. And here is pi over 2. So our outputs are going to come from the first and the fourth quadrant, but they have to be between negative pi over 2 and positive pi over 2. So any angles that we grab are going to be acute, either positive or negative. Okay, what do I mean by that? Okay, let's talk about the inverse sine of radical 2 over 2. That's a familiar ratio to you, right? Which angle has a sine ratio of radical 2 over 2? Say it out loud. Okay, 45 degrees. Now we're going to go in radians. So I'm going to ask this again. You answer in radians. Which sine ratio has, which angle has a sine ratio of radical 2 over 2?
Pi over 4.
So our answer is pi over 4 and only pi over 4. I know that the sine is radical 2 over 2 in an infinite number of places, but we have to stick to this range right here anytime we see that inverse sine. Now, if I ask you for the inverse sine of radical 2 over 2, but it's negative radical 2 over 2, what would we say? I know that 7 pi over 4 is in the fourth quadrant, but it has to be in between these values. So instead of 7 pi over 4, we would say negative pi over 4. Okay? Your answers to inverse sine are either going to be rotated up into the first quadrant or negative in the fourth quadrant. So your answer here was pi over 4, negative radical 2 over 2, negative pi over 4. It actually makes it easier. Okay? It's always going to be that acute angle. Okay? We'll do more examples, don't you worry. Inverse cosine. Okay? Now you aren't familiar with the graph, but this is what inverse cosine looks like. Okay? It looks very similar to sine, but it's a little bit different. Once again, what's the biggest cosine value we get on our unit circle? 1, what's the smallest value? Negative 1. So this graph bounces in between negative 1 and 1. Okay? We'll do more with that on Tuesday. Okay? If we were to make this into an inverse, it would look like this. Is that a function?
No.
It's not a function. We have that same issue. Okay, so if we erase pieces of it to where we have a unique chunk that doesn't repeat, we're left with this. I know you don't really care about the graph, but this is what we need to know about inverse cosine. Once again, we can notate it as arc cosine or inverse cosine. Once again, it has a domain from negative 1 to 1. Our inputs are from negative 1 to 1, just like those values on the unit circle. But now our range is different. It's 0 to pi. We're talking about the unit circle. 0 to pi covers which quadrants? Okay, we are grabbing values from the first and the second quadrant. Well, some of you may be thinking, well, why can't sine and cosine have the same range? Like, that bothers me. Okay, well, let's think about it. If we wanted sine to have the same range, go from first and second quadrant. What's true about the sine in the second quadrant? They're positive. Okay? So we're not getting any negative sine values, and that's not okay for the outputs of our function. Okay? Vice versa. If I wanted arc cosine to have the same range, first and fourth quadrant, what's true about cosine in the fourth quadrant? It's positive. Okay? So if we're grabbing values from the first and fourth quadrant, they're all positive. There's no negative. We have repeated values. That's not okay for a function. Okay? So cosine is kind of the oddball, but it's also kind of nice because we don't have to think about negative angles. So, for example, if I asked you for the inverse cosine of radical 2 over 2, I'm asking you which angle has a cosine ratio of radical 2 over 2, what would you tell me? Which angle has a cosine ratio of radical 2 over 2? Pi over 4. I know you know it. Okay, I'm asking you the easy ones for a reason. Okay. Now, if I ask you for the inverse cosine of negative radical 2 over 2, okay, to fit our range, we're going to have to go into the second quadrant. 3 pi over 4. Okay. And then lastly, we have our tangent. Okay. I'm just going to show you the inverse tangent graph. It looks like this. Okay. Once again, we have the kind of thing where we have to take our tangent graph, and in order to take the inverse, we have to restrict it. So the tangent graph actually looks like this. Okay, over and over and over and over and over again. But for our inverse, we can only have one of those swooshes. Otherwise, we wouldn't have a function. Okay, I'll teach you how to graph those in a week and a half. The inverse tangent does have a domain of all real numbers, which is nice. We can plug anything into inverse tangent, but its range is, I'm going to say, similar to inverse sine. We still have negative pi over 2 to pi over 2, but we can't include those endpoints because tangent's undefined there. Okay. So brackets for inverse sine, parentheses for inverse tangent, but we still have the same quadrants. I'll raise this up a little bit for you. So like our sine function, inverse sine function, we are going to be grabbing positive values from the first quadrant, negative angles in the fourth quadrant. We're going to either rotate up to the first quadrant positively or down to the fourth quadrant with negative angles. our inverse tangent of 1. Which angle has a tangent ratio of 1? Pi over 4. Funny how I'm asking like the same angle, right? Trying to pick the easy ones. At pi over 4, our tangent ratio is 1. So the inverse tangent of 1 equals pi over 4. If I ask you for the inverse tangent of negative 1, we have to rotate to the fourth quadrant, but in the negative direction, so we can fit the range. Okay? In my opinion, it makes it easier for yourself. Think of the first quadrant angle, but if it's negative, make the angle negative. Okay? So we're going to try some examples here. Here are our first two. Go ahead and write both of them down. Okay, what kind of angles have a sine ratio of 1/2? Pi over 3, pi over 4, pi over 6. Which one? Pi over 6? Pi over 6 has sine ratios of 1/2. So since it's negative 1/2, and we're talking about inverse sine, our answer would be what over 6? Negative pi over 6. Good. What kind of angles have a cosine ratio of radical 3 over 2? Pi over 6 angles, right? But we're talking about an inverse cosine. So the inverse cosine of negative radical 3 over 2 would be what pi over 6? Okay. Remember, the cosine comes from the first and the second quadrant. So we're going to have to call this 5 pi over 6. Okay? Cosine is the oddball out. He's the one that's different. Okay? He wants to stand out. Inverse cosine will have answers from the first or the second quadrant. Inverse sine of 2. Can't make it go down. Where's that? I don't have my little extend page button there. Inverse sine of 2. Guy just said, can't we not do that because our domain is negative 1 to 1? He's exactly right. We cannot do that. Because 2 is not in our domain. Thank you, Guy, for catching that for us. We already did that example. Inverse cosine of negative 1. Where is the cosine ratio? Negative 1. Pi. Very good. Last but not least, the inverse tangent of negative radical 3. What kind negative angles have a tangent ratio of radical 3? Pi over 3. Okay? Since we have a negative ratio, though, and it's inverse tangent, we have to rotate to which quadrant? We have to rotate down to the 4th quadrant. So this answer would be negative pi over 3. Okay? If you don't do your homework tonight, you're going to be in a world of hurt. You have to practice these rules. Okay? I'm telling you right now. Last night was not a good homework night. I had like 7 or 8 of you who didn't do your homework. Okay? I can forgive you. It's fine. We got to do our homework tonight, though. Otherwise, tomorrow is going to be not as enjoyable for you. Okay? It won't be as meaningful. Okay? I need you to practice. Now, go ahead and get out your calculator and put it into radian mode. I just want you to understand the function of those buttons on your calculator. Okay? Okay? Now, yeah, I had an issue with the inverse sine of 2. Here I have the inverse tangent of negative 8.45. Remember, inverse tangent has a domain of all real numbers. Anything can be plugged in. So go ahead and find your inverse tangent button. I think it's just second and then the tangent button, if I'm not mistaken. So put the inverse tangent of negative 8.45. Sydney, what do you get?
I got negative 1.453.
Okay. Go ahead and try to put in the inverse sine of 2. Error domain. Okay. 2 is not in the domain, so it gave you an error. Okay. So if you accidentally do that, like if you're on a calculator problem and you plug it in and it gives you that message, don't freak out. It just means that number is not in the domain. It's undefined. Okay. Okay. So the last piece of our lesson, we are going to be combining trig and inverse trig functions together. Okay. Now, sometimes it's glorious and they cancel out. Sometimes they don't cancel out. Okay? Like the square root of x squared, man, we cancel that all the time, right? The cubed root of x cubed, no problem. Okay? But since our inverse trig functions have such specific domain and ranges, the stars have to align. Okay? So, if inverse sine and sine are going to cancel out, then we have to make sure we have that correct domain and we have to make sure we have that correct range. Sorry, my pies look funny. The formatting got weird. But you know that they're pies, so it's fine. Same thing with cosine and inverse cosine. If they are going to undo each other, we have to make sure that that domain is to the specific negative 1 to 1. The range is that 0 to pi. If those numbers aren't in those intervals, then we have to do the problem piece by piece. I'll show you what I mean by that. And you probably can start writing down what the rules for tangent and inverse tangent are to cancel each other out. Okay? This rule will be able to happen anytime. Yay! Okay, because we have a domain of all real numbers. But if this is going to be able to cancel out, we have to make sure that y is between negative pi over 2 and pi over 2. Essentially, you have to make sure that your input is okay and that your answer, your output, is a legitimate output for the inverse function if that's the case. Okay? If I ask you an inverse cosine problem, there is no way that your answer can be from the third quadrant. If I ask you an inverse sine question, there is no way your answer can be from the second quadrant. So you're just going to have to think about whether the functions can undo each other, and if not, we have to go piece by piece. Okay? This is basically a shortcut like the cubed root of x cubed, but it can't happen every time. We have a few examples left, and then I'll send you on your way. Okay? I'll tell you what, though, these will be like the last examples of the week because tomorrow we're going to do an activity. So if you can just hang with me to 9:07, then the rest of the week is downhill. All right. So the tangent of the arctangent of negative 5. Are the stars aligning? Look at what you just wrote down for arctangent. If tangent and arctangent, these are no calculator things. If these are going to cancel out, we have to make sure that this number is real, right? Anything can be plugged into arctangent. Anything can be an output for tangent. So this is a case where these cancel out and our answer is negative 5. Ooh. Okay. I didn't even think to check these. So that's the arcsine of the sine of 5 pi over 3. Okay, ultimately, what is our outer function? What is the outside function? Sine or arcsine? Arcsine. What kind of answers do we get from an arcsine problem? Quadrant 1, quadrant 4, right? But what kind of numbers from quadrant 4? Negative angles, okay? So it is not okay, don't do this with me. We cannot cancel these out to be 5 pi over 3 because we can't have an answer of 5 pi over 3. That's not okay. So instead, what we're going to have to do is answer this piece by piece. Please tell me, what is the sine of 5 pi over 3? Negative what? Negative radical 3 over 2. So now we have the question, what's the arcsine of negative radical 3 over 2? Well, we are not going to rotate to the first quadrant. We're going to rotate negatively to the fourth quadrant. So our answer is negative pi over 3. Yes, do you have a question?
I was just confused on like why couldn't we go straight to that step? If we could figure out the negative based off of the sign.
So you're saying like you don't want to do the middle step, you just know that it's negative pi over 3?
I'm asking why did we have to do that step?
I just want you to understand like how it would go piece by piece. Are you saying like you could do some of that in your head?
Well, I got the negative pi over 3. That's why I was saying that for the middle step, but I didn't know why.
So you can probably get to negative pi over 3 without that middle step, but some of us need the visualization of doing the inside first and then doing the outside. Okay. All right, we'll do one more example. Let's go down to, well, here, okay, so I lied. 2 examples. Cosine of inverse cosine of 3. Can they cancel? Why not? Okay, 3 is not in the domain of inverse cosine. If you tried to put inverse cosine of 3 in your calculator, it would spit out that error. Okay? We have to be aware of when that happens. That's bigger than 1, so that is not okay. Very good, Monique. All right, so this is our last example right here. Negative 3/5 a unit circle ratio? No. What do we do? What did we do yesterday when we didn't have unit circle values?
So reference triangle.
We used a reference triangle. So let's focus on this right here. Our output for arc sine of negative 3/5 is going to be an angle. Where would that angle be? Say it louder. The 4th quadrant. We have inverse sine, that's negative. We are going to be in the 4th quadrant. Our sine ratio of this angle is 3/5. Well, we have a right triangle, hypotenuse of 5, side of 3. Okay. So this is theta. What's the cosine of theta? Riley, what was your question?
I just have to do problems like that.
Okay. Yes. We need to practice.
Yeah.
And tomorrow we're going to take a day where we're going to do an activity to help strengthen our skills in this. But you need to practice for sure. Okay, this is a topic that you touched the surface on in Algebra 2 that we're really taking deeper. Okay? This is pre-calculus, people.
Oh, yeah.
Oh, yeah. Okay. So tomorrow, you'll walk in and I'll give you like a little entrance ticket. It was going to be an exit ticket today, but we had more examples that we needed to do. We'll check your homework. We'll do an activity. I'll give your quizzes back tomorrow. I've graded them all. They're in the grade book, but you'll get them physically back tomorrow. Okay? Okay. Happy Wednesday. So one of you hit the light switch on your way out, please. Thank you. You like this stuff? Is that what you said, Max?
Yeah.
Good.